The University of Colorado Boulder is one of the top public research universities. Research computing at CU provides computational resources to support all types of research that have large-scale computational needs.
Here at CU, we support many dozens of research groups from nearly every department on campus. And based on that, as we were thinking about the design of Summit, architects from Intel and Dell EMC helped us to determine what sorts of components would provide a much wider range of different capabilities in terms of computation, in terms of the network, in terms of the storage, to support just a vastly greater range of applications.
The architecture within Summit consists of 4 computational partitions. There's what we call the Haswell partition, which is the Dell EMC PowerEdge C6320 partition of the system that's based on the Intel Xeon Haswell architecture. The E5-2680V3 processor provides good balance not only in price or performance, but also in clock speed versus number of cores per processor. The second partition of Summit is a GPGPU accelerated partition based on the Dell EMC PowerEdge C4130 architecture. The third is a high memory component, and this is largely to service some of our partner institutions that really need a lot of memory in one box. And then the fourth is the Intel Xeon Phi Knights Landing platform, which is a CPU processor, not a co-processing architecture. Rather than having to worry about going out to an accelerator, they can just program right on the machine. So we're really excited to see that be a simpler architecture for our users to program against. All of the compute sits on the Intel omni-path architecture fabric that we've built up as the interconnect that provides 100 gigabit per second connectivity to each host. New technology, like the Intel omni-path architecture, like the Intel Xeon Phi Knights Landing, provide cutting-edge performance. Summit provides more than twice the floating point performance in about half the data center space, power, and cooling when compared to our previous generation system. We're expecting about 400 teraflops of performance from this machine.
Summit will definitely have enough juice to run the majority of big problems that our researchers need to get into.
I study galaxy formation, and we run these simulations for a long time. They take 100,000 to 1 million CPU hours. Fortunately, with a system like Summit, you're running simulations on 512 to 1,000 cores. With Summit, we can build more realistic galaxy simulations at higher resolution and with new physics.
Quantum physics is everywhere in our life. It describes pretty much every experimentally understood phenomenon. Your camera, the phone, computers, internet has some kind of basis in quantum physics. Having Summit, I can answer questions about high-energy physics and get more precise predictions than what was possible without Summit.
We do research on numerical simulations of turbulent flows. We have projects on combustion for propulsion engines, combustion for wildfires, geophysical turbulence, particularly in the ocean. Summit will allow us to better use computational fluid dynamics, and that's largely because of its increased computational capabilities. I think it's rare to have such a powerful computer so readily accessible.
What excites me most is that we want to bring researchers together and they focus on their research and we focus on providing the computational infrastructure for them.
The thing that I love about HPC is when somebody's using one of our systems and they come up with a cool new result, or they make a fantastic new discovery that just would have been completely out of range otherwise. It's awesome.